Dipankar side.
Hilbert space is the thing that is used in our quantum system. Measurement is very important thing. I will describe in details what is the measurement later. But the important thing is that in 1958, Dirac proposed some notation that is very useful in quantum computing, that is called bra and Ket notation. If the bra is the transport conjugate of Ket, so I will come in details. So actually it is represented in this way. 0 is represented in 0, 1 it is represented in this way. So that is what I was saying, that any vector A, if I write any vector okay, it's not showing, fine. So if it is A is the vector that can be represented as AX, I, AY, J plus AZ. So it is the real space where we represent the vector. So you know that if I dot I is equal to J dot J equals to K dot K equals to 1, then we call it as a normalized. And if it is 0, if I dot J equals to J dot K equals to K dot I equals to 0, we call it as orthogonal. So if both are satisfied, we call it as orthonormal. So we are not going into the details of mathematical part, but in Hilbert space actually, if it is mapped into the three bases, maybe that you may consider that psi 1, psi 2, psi 3. So psi is represented as superposition like C1, psi 1, C2, psi 2, and C3, psi 3. So actually it is we are finding a volume. You can put not single integration, three integrations will be there. So actually if we find that delta ij, if delta ij is 1, then we say that if I equals to j, we can it will be bra psi I psi j will be equals to 1, otherwise it will be 0. Then it supports the orthogonality property.
So what is the three bases you just mentioned?
Three bases means if we consider the three in real space, what was the basis?
Canonical basis or any kind of basis it can be. I mean, you are talking about canonical basis or any kind of basis?
Any kind of basis.
Okay, canonical basis is the simplest of the kind. That is why I am saying that if you are plotting it into 2D, you can have only two bases.
Right.
So you are still
Here also,
plotting
if you are also
in
two bases is possible, three bases you can use, that is possible.
No, but it is in 2D.
Yeah, I have shown as an example.
Okay.
It is a sample.
Actually, it is in 3D. You are showing in 2D.
Yeah.
Okay.
So for 2D actually it is a complex vector space. So we can if we say that this is 1 and this is 0, then suppose this is the vector, so I can represent this as alpha 0, beta 1. Beta this is called actually Ket notation. So we should say that alpha Ket 0 plus beta Ket 1. So this is in matrix form we can write like this. So if we represent 0 qubit can be represented as 1 0 and 1 is represented as 0 1. Okay. So this is the representation of the 0 and 1 state for the qubits. So as I told that it is it follows the linear property. So we can represent if it is 2, then we can multiply with 2 alpha, we can represent as 2 alpha. So 2 alpha beta we can write in the matrix 2 alpha 2 beta. This is very simple thing. So actually this we can consider the polarization of the proton, or we can consider the spin of electron. So if it is up, we can consider it as 0. If it is horizontal, then we can consider as 1, as last diagram we have seen. Or if you consider the spin of electron, if it is up, it will be positive vertical spin, that is 1. Down, then you can consider as 0. So this is the there the basis will be 1 and 0, that is the fixed basis. So we can represent any qubit like psi equals to alpha 0 plus beta 1, right? Okay. And always you should remember that alpha beta is the probabilistic value. So alpha square plus beta square will be 1. Sum of the probability always will be 1, right? So it will be 1. Now, if we consider the 2 qubit system, 2 up spin means we may consider 1 1, 1 up then down, that means we may consider 1 0, 1 down up, 0 1, down down means 0 0. So we can represent as psi as A down down plus beta like this, right? The superposition of all the states. So we prefer with the computer science background or electronics point of view, we can represent 0 0. So A 0 ket 0 0 plus B ket 0 1 plus C ket 1 0 plus D ket 1 1. So A square plus B square plus C square plus D square, the probability sum of the probability will be equals to 1, right?
So are we trying to convert the digital number system to the quantum one? I mean, like this fashion?
Obviously, we have to do it, na? Otherwise you cannot do it. You cannot process further. You have to.
So the basis of the quantum computing itself is the digital one.
Yeah, digital concept is there, but not exactly same as
transforming. We are transforming.
Yeah,
so I cannot have more representation than the digital
Yeah,
one.
definitely. Computer system.
So in that case, how can I generate extra something? I mean, when which I mentioned there, that it doesn't mimic directly the natural thing. So when I'm again using that digital information and transforming into the quantum, then how I get that extra thing?
This is the advantage. I think unlike your classical computer, you can use the superposition thing. In the classical computer, can you use the superposition? Is there any concept of superposition? No. One qubit can represent the multiple information. Huge information can be stored in a single qubit. That is the major advantage of quantum. And speed thing also will come there.
Can digital system be represented in quantum? Quantum can be represented in digital system.
Yes, possible. Not all the things. All the things. For example, I have told that you are asking that quantum system can be represented in the digital system. Superposition you cannot do it. Directly. Can you do it? That is, you cannot do it. But vice versa is possible.
Vice versa is possible.
That is what I was saying. So, if I say the 2 qubit basis state, it can be represented as 0. This is called tensor product. This is called tensor product. So 0 tensor product 0, 0 tensor product 1 will be 0 1, 1 tensor product 0 will be 1 0, and 1 tensor product 1 will be 1 1. So we can say this one as 0, this one 1, this one you can write even using ket 2 and this one ket 3. So in matrix form, you can write this one as 1 0 0 0. This one can be represented as 0 1 0 0. This one 0 0 1 0, and this one 0 0 0 1. What is tensor product? If you can remember that 1 0 tensor 1 0, that means it will be 1 then 1 0 then 0 again this will be 1.
Please explain once. 4000 matrix is coming 1, then 4 0 or 0, then 1, then 0 0. Yes, that's what.
This one actually this one. I am explaining this thing. Actually, suppose you are what I told that 0 can be represented as 1 0. So 0 0 means you have to perform the tensor product between 0 0. So matrix form 1 0 1 0. So 1 0 1 0 means what? 1 1 0 0 1 0. So you will be getting 1 1 then 0 1 1 1 1 0 0 0 1 0 0 0 0. This is the thing. In this way you can solve this.
On the last one, why is it not 1? Why is it 1 not 0? It's the same as second one.
Second one.
The upper one.
This one. This one.
Yeah. Now that's not 1 is equal to 0 1. Now the last one, why didn't 1?
The last way notice.
Last is this one.
It's the same with the second one. Then why it's 1 1 instead of 0?
Well, it will be 0 because what is the matrix of 1? What is the matrix of 1?
0 1.
This is 0 1. So 0 1 and tensor product 0 1. You will be getting this thing. Any other? You are asking something else?
Actually, we are asking like 1 1 XOR. It is look like XOR. That's
It is not XOR. It is tensor product.
It is not XOR.
It is not XOR. This is tensor product that I told. So if you combine all these things, you will be getting what is that? Unit vector. So this is the unit vector. Unit matrix that you will be getting. Similarly, n-qubit system can be represented as this thing. Summation of k to 0 to k to the n minus 1 a k. If you put 0, a0, k will be 0. If it is 1, 1. If it will be 2 means you know 1 0. See, so 1 1 like this, and the probability will be 1. So this is the representation of n-qubit system, right? So as I already have told that the quantum mechanics is probabilistic, is represented as alpha 0 plus beta 0. So if we measure this, the thing is that it will be the states will be destroyed. Means suppose there are 3 chairs. Now, the probability of sitting in this chair for me may be 0.8. This one may be 0.15. This one may be 0.05. So, if I sit here, then is it required? This state will exist? No. I am sitting itself here. So, if you measure the quantum state, then it will become the classical one. So that means there will be no state. Quantum states will exist. This is the thing regarding the measurement. Okay. So if we want to design some small circuit using quantum gate, how we can do it? This is simple quantum work where, so if we pass 0, I will get 0. If we pass 1, I will get 1. If we represent A 0 plus B 1, same thing we will be getting, right? But this is called quantum not gate. Gate actually in terms of quantum. This is 0, this will be 1. 1, you will be getting 0. So if it is A0 plus B1, you will be getting A1 plus B0, right? So if you represent using matrix, this is 0 1. So 0 will be converted into 1, 1 will be converted into 0. So matrix will be this 0 1 1 0. Right? So now the thing is that if you apply x gate on 0 cubic, I have told that this is a matrix for x, this is the matrix for representing 0. So if you multiply, you will be getting this. What is this? 1. If you apply x on 1, multiply, you will get 0. So this is the thing that how it works. Can you tell me that if I apply 2x gate, what will happen? Because
Not of
not of now. Actually, not only for this gate, the quantum gate, this is the property that if you apply the same gate twice, you will be getting the identity matrix. Okay, so for any gate, this must be satisfied.
মানে অলওয়েজ
Always.
এন্ডেড পর এন্ড লাগালে মানে
There is no concept of AND gate, sir. There is no AND gate concept here.
অনলি নট গেট
Not only on not gate, there are other gates also. Will be counted.
So always to be number of input and number of output might be same.
So you can think in this way also. A0 plus B1 will be after this. It will be A1, A0 will be 1, this one will be 0. So A1 plus B0. After this one will be again A0 plus B1. And this is what I was saying, that xx, if you multiply, you will be getting this matrix. What is this? I. So there are 3 gates with basic gates that is known as Pauli gates. So x gate I have already told. So that is represented as
বেশি নাম্বারও বেশি একটা হলো সেখানে আমি তাই এটা
fine. Actually, it is actually I can consider this one as the gate 0, gate 1, raw 1,
সিকোয়েন্সিয়াল
raw 0, raw 1. Again I am repeating.
এটা আউটপুট সেটাকে ইনপুট করতে হবে
Here I can write.
আউটপুট লাইন
ও মানে মাঝখানের কাজটা
আজকাল কাজটা ব্ল্যাক
This is actually not permanent marker, right? No, sir.
নো
So, if I represent, the rule is that if it is GABA, this is gate, I have already told. GABA is the transpose conjugate of gate or vice versa. So, if I represent this thing, I will convert, I will consider gate in the place of bra. That means it will be gate 1 0. Then this one is 1, so I will consider this thing. So this one will be bra 1, right? Clear? I am again repeating. This is this one I will convert into the I will consider gate. So gate 0 bra 1, gate 0 bra 1. Similarly, this one is 1. So gate 1, then bra 0, bra 0. This is the representation of x gate here. So if I perform x0, what will I can write this one. This is the already I have shown. Along with this 0 will be there. So 0 now bra 1 and gate 0. That means it will be 0. So what is the remaining thing? Bra 0. Then last part is Bra 0 get 0. So bra 0 get 0 means it will give you 1. So that means you are getting 1. Is it clear? Anyone is having doubt?
Not the logical implementation of the NOT gate.
I am saying this is this one will be multiplied with this one, so this one will be 0 plus this one will be 1 this one will give you 0. So ultimately this one will not exist. So this one will be 1 and this one is actually 1. So that means we will be getting 1. Similarly for y get, same way that I have told here, you may get y equals to minus I, bra 0, get 1 plus I, bra 1, get 0. So if you apply y on 0, you will be getting I1. Z also, this is the matrix of Z, so you will be getting in the same fashion, this is the Z representation. So if you apply Z on 0 or 1, you will be getting this. So actually Z is changing the phase, Y is changing both phase and the bits, with flip and base figures. So now this is the simulator. If we get time, I think in the lab we will show you how to use this. So if it is 0, you will get what will be the output? As already I told, 1. So 1. So you are getting get 1 here, and the amplitude also will be 1, and here you will be getting 100%. Similarly for 1, it will be 0. Okay. Any doubt? Time is very less, that is why I will something. So if you apply y get, if it is 0, what will be the output? I will told 1, and this one will be 1. But if you apply on y, it will be minus I. It will be 0 plus minus I. Both phase and the midfield, both will be. Similarly for Z get also. If you apply on 0, it will be 0, and if you apply on 1, only it will be minus, nothing else.
The Z gate is equals to previous gate.
This same as this one. 1 will be 0, 0 will be minus 1. Only there will be a phase. And this is the real quantum gate, that is called most interesting Aramat gate. If you apply Aramat gate on 0, you will be getting the superposition of 0 and 1. Both 0 and 1 you will be getting. If on 1, you will be getting 0, get 0 minus get 1 by root 2. So A0 plus B1, I can write this 0 is, I have told that this, and 1 is this. So if you add this thing, you will be getting A plus B by root 2, A minus B by root 2. If you represent in the matrix form, this is the matrix. 1 by root 2, 1, 1, 1 minus 1. 0 plus 1, 0 minus 1.
One minus one.
one A plus.
Any doubt?
One minus one. How it's the matrix.
Yeah, 0 plus 1, combination of 0 plus 1 by root 2. Here also 0 minus 1 by root 2. So if you represent like previous thing, this is the representation. If you do it in hand, you will be getting this thing 1 1 1 minus 1. So all are 1. So brow 1 will be converted into cat 1, cat 0, brow 0 will be converted into cat 0, and then it will be brow 0 like this. It is very simple. I think you can do it. I am not going into the details. So if you apply on 0, h of 1 0 means what? You will be getting 1 by root 2 1 1, right? You will be getting 1 1. 1 1 means what? 0 1 plus 1 0. So combination of 0 plus 1, right? So 0 plus 1 by 2, right? Similarly, if you apply on 1, everything is same except this one minus. You will be getting minus. As I told that for every gate you will be getting ultimately what? H will be identity matrix. It will give you I. This is the thing. Previously, if you notice that it was 100%, now it is 50%, 50%. 50% chance for 0 and 1. And 1 by root 2 means what? 0.70 something. Right? Here, if we apply on 0, that means we are getting this. If we apply on 1, we will be getting this. Only the minus is here. Minus 1 was there in the matrix. You can remember this. Right? So this is the way. Now, if you apply to Hadamard, as I have told, it will be 100%. What it will be? It will be H and it will be I. So 1 on I, that means ultimately 1. So you will be getting 1 here with 100% probability. Right? Similarly, there also on 0. So what will be the output for this? H, it will be I. I. So you may consider it will nullify each other. That means 0,
It is 1.
it will be 1. Then Z, what is Z1?
Minus I.
Z minus 1.
Z of 1.
Minus.
Similarly, you can apply Y and then X. 1 on Y. I think you can do it, right? All these things. I have got it.
Inversion of I, because for 1 in Y gate you will get I.
I means ultimately if you pass 0 over I, what will you will be getting? That is 0. So actually this is the unitary matrix. Unitary U dagger U equals to I. Actually what is U dagger? U dagger is the U transpose and then conjugate. So yeah. So that means if it is A, B, C, D, it will, if we want to find the U dagger, we will be getting A star, B star, C star, and this like this. Okay, so it is called unitary matrix. If it is alpha beta can be written as U and then alpha beta. Now, so as already I have told that X dagger will be pi. So X dagger, if X is this one, X dagger also will be this one equals to X. You can do in hand. I am not showing due to shortage of time. Then similarly H dagger H also will be I. And similarly for Y gate and Z gate also you can do it. The advantage is that for unitary matrix it preserves the length. That means if you then some side, then you will be getting the length of side itself. Okay, so that is the advantage. Now come to the swap kit. Swap means what? Change of the, so if it is AB, it will be BA. So if it is 0 0, it will be 0 0. If it is 0 1, it will be 1 0. 0 will come here, 1 will come here. 1 0 means 1 will come here, 0 will come here. So 0 1. 1 1 means 1 1. Same.
Please go to the previous slide. How to read that one?
Length of U, then the side.
No,
Get
that
side.
after equals to how to read that? Oh, that is the.
This is length.
That is totally
Totally length, yeah. So what I was saying here, from there, how can you get the matrix? How will you get the matrix? The simple way is that if we represent I4 as this is unit matrix, right? Now, here we are swapping what? Here, if you notice that 0 will be given 0, so 1 and 2 will be swapped, right? 1 and 2 will be swapped. So that means I can easily construct the matrix. Just I will swap this position. This is for 1, 0, this is for 1, this is for 2, and this is for 3. So I will swap this 3. So that means if I want to get the unit matrix, corresponding matrix of the swap gate, I can write 1 0 0 0. This is a simple way. Then 0 0 1 0, 0 1 0 0, 0 0 0. This is the simple way of getting the matrix representation of this what we are doing.
That's the way to remember all.
Remember? Yeah. If you want to do that, you have to do the calculation.
Why the U is written? What is the significance of U? What U stands for?
For matrix,
That's
so when you will be applying on some other state.
no. The U is written there. U swap. What U signifies?
U is the way representing a swap gate. That is, U is the swap operation on 0 0. You can use any symbol. That's not the issue. So this is the, if we apply swap gate, obviously this will be the output. That CVD is 1, 0, this one. It is 0, so 0 will be what? 1. And 1 will be, after addition, what it will be?
And operation দিলে or operation
First will be 0, next will be 1. So 0
logic দিলে or logic
and 0. So, sorry, this one 1 and this one was 0. So that will be swapped. So it will be 1 0, right? What is the element? Right?
X becomes 1 and X,
Right.
this one X becomes 1.
Right. So this one will be swapped. Like this. Now, C not get, that is very important get for very important part of it. called control qubit, it is called target qubit. So based on the control, I will decide. For example, if it is 0 0, that means this one 0, this one. If it is 0, it will not be changed. If this one is 0, this one is 1, then also there will be no change. But if this one is 1, then this one will be changed. So if it is 1, it will be converted from 0 to 1. If it is 1, 1 will be converted to 0.
সামনেটা চেঞ্জ হবে
Okay. Similarly, also matrix also you can form in the same way as I have shown in the last. This is the matrix you will be getting in the similar fashion, because here you can see that only this one and this one, 2 and 3 position will be changed. So that position if you swap, you will get the matrix, full matrix. We can do in this fashion. That is, if there is serial, then we do x, y, this 0. So x, what will be that? If I apply on 0, y of 0, what will be the result? I of 1, I get 1, right? If we apply x on this, what I will be getting? 1 will be converted into 0, so I 0. Very simple. Similarly for 1. Any conclusion? Any conclusion?
For YK, what
Or
if we
why?
apply 0, what will be the output? Minus side or
That I showing on the previous slides.
that's minus side. If I put 0.
Here you will apply yes, right. But here 1 not 0. If you apply certificate, what you will be getting? This one will give you.
So sir, if I apply 1 in YK inside,
If you apply 1 on y get yes.
then it will be I.
For 1 it will be minus n. For y it will be minus n. That is why you are getting minus 5. If it is parallel, how we can compute? We will write in this fashion. A XOR B we will perform and we will perform tensor product of A and B, and tensor product of psi 1 and psi 2. That will give you the result. How you can do? For example, this one. How will you compute this one? There is nothing means you may consider I is there. I is there. So I is there means H tensor I, 0 tensor 1. So what is the representation of H? This is the matrix for H. This is the matrix for I. And 0 tensor 1 is 0 1, 0 1 is 0 1, 0 0. And this is the tensor product you calculate. You will be getting this one. This one means what? Root 2 1 upon 2, 0 1 plus 1. Any doubt? Yes.
So please recommend us some resources from where we get this lecture notes or anything so that we can learn this. So then only it will be helpful for us to carry this forward. Okay, sir. No sir, we are not asking about PPTs.
You are asking for the books.
Books or yes sir, yes. Or e-resources, everything.
I will give you the details of books we have on the slide.
Thank you, sir.
So, but nowadays main source is Google. Everything will
So
find it.
actually, when Google says different type of learning, so which one is right? So that we have to
Okay, so similarly, if H followed by the synoptic, this is very interesting. There is something. If you calculate same fashion, I will follow that C naught of H tensor product I and 0 tensor product 0. I will perform the operation matrix multiplication and I will get this state. But this state has some importance. That is called belt state. Actually, after getting this one you cannot represent using as a product of tensor product of two states, two matrices. You cannot represent it as that. That is why you cannot separate it. They are entangled. That is what we are showing in the video. This is called entangled state. 0, 0 and 1, 1, it is the entangled state. Even if it is previous one, if I tell you that is 0, 1, 1, 1, that means 1 can be taken as a tensor product along with 0 plus 1. But here you cannot do it. Similarly, 1, 0 and 0, 1, that is also another belt state. So you cannot change it. So that is the real example of entanglement in quantum computing.
The same logic is unit distance vector to be maintained.
Unit distance?
Unit distance vector to be maintained. The state should be. The last section is distance between the two vectors.
Yeah.
And 0.
But this is actually representation using tensor product. These two are not totally same.
The state of the
State of the, but you cannot represent using as a tensor product of two things. But there is the concept of unitary matrix that we were talking about, right?
So we are asking to vector unit
Unit distance vector.
unit distance between the two states.
Unit distance between the two states.
Because 0, 1, 1, 0 cannot be represented like this. 0, 1, 0, 1 and 1, 0. There is also unit distance. And 0, 0, 1, 1. That
But
is also
unit distance is here as important from quantum point of view. So as I told, in the simulator we will be getting this same output. That if it is 0, 0, if it is 1, so 0 means it will be 0. So 0, 0 will be the output with 100% probability like this. When it is 1, so this 1 will be 0. So it will be 1 here. Similarly, 3-qubit system. Here, the control is this one. This is the target qubit. So based on the middle one, the decision will be taken. So here there will be no change, 0, no change. There this is 1. So as this is 1, this 0 will be converted into 1. So it will be 0, 1, 1. In this way, you will be getting the state change. And based on that, you can, in the same fashion as I told, you can write the matrix also. Unlike last time, because 8 cross 8 matrix, 4 cross 4 matrix, it will be 8 cross 8 matrix. So, here also in the same fashion you can simulate. You will be getting the output as I told, based on the middle one if it is 1, this one will be 3. So, this one will be 0, then 1, then this one will be 0, 0, 1, 0. Now, this one, what will be the output? This is 1, this 1, so 1 based on this 1, this 1, so this 0 will be converted to 1. Then this is 1, so this 1 again will be changed to 0. So this one will be 0, this one will be 1, this one will be 1, 1, 1, 0. Like this. Okay, so these are some more examples. It will be better if you do in the lab. Okay, that I told these two examples. Just here the control is here. So based on this, this will be changed to it or not. That we will be deciding. Hopefully get that is, if both are 1, then only it will be changed. Otherwise it will not be changed. That is. So these are the things we will be doing in the lab. So actually, as I told that use both are living person. Till that they are living alive and they are very renowned scientists. So actually, use I have told that I have shown that how the quantum algorithm performs better than the best classical algorithm. Okay, and so use algorithm is very popular. It was published in 1992. I am not going into the details of the algorithm. And that is Peter Shor. He is also living person. Peter Shor, so as I told that that was the number, use number. That actually these are the two prime numbers. If you multiply, you will be getting this. So that prime number. So if you follow the source algorithm in quantum computing, you can easily tell what will be the prime factors. But this itself will take some hours to explain. So I am not going. If you are interested, you can go through it from different sources. I told that searching in routine time. So he is also living in India. So he is a very renowned scientist. He has shown that by changing the phase, we can search any element in the quantum computing by routine time. There are different cryptographic algorithms. You know, one very popular is Salsa. I think all of you have heard. So Chacha and Salsa, I am not going into the details. But the thing is that the important thing is that Google from since 2013 they are using Chacha instead of RC4. And Chacha is still not regular, but we are also working on this. My research scholar Somen, he is doing on that. Somen and Sorvani, they are working on this and they have got something. Within few months, I think our paper will be published on that, how to attack on Chacha. But don't get afraid of this because till date more than 1000 qubit quantum computer has not come. So you are safe. Okay, so this is the, I am not explaining this in details. How it works, the covert algorithm. The only thing is that this is not our work, but this is the existing thing. Your main target will be that to follow the NIST standard. There are some standards that you cannot use more than this number of gates, this number of gates. There are some standards are there. So, following NIST standards, for Chacha, the C-node requirement is this, Toffoli gate is this, and the qubits requirement is 1024. We are 433 qubits. So, and IBM has told 1000 or more will be in 2024. We do not know what will happen. So, but according to the NIST standard, you cannot use the Toffoli gate. There are some restrictions. So, we have to give for gates. Okay, so this is the actually requirement. till date for Chacha 12 and Chacha 20. After one iteration. For all iterations, this is the requirement. Use.
Chacha 2020 stands for what?
Chacha has two versions, 12 round and 20 rounds. Chacha has two versions. So this is actually NIST standard. That you cannot go more than that. So this is still now it is 2,290 it is the maximum one. I am not going into what is that max depth or GMT. There are some calculations I am not doing. So actually now we will go to the lab for better understanding. I think we could able to give some idea about what is the limitations of classical computing, what is the advantage of quantum computing, and what are the different types of gates that is used. There are, I am telling you, there are other gates also, like S gate, T gate, there are other gates also, but we can design any circuit with the gates which we have discussed today. These are the basic gates. And then we have discussed about the different cyber security aspect, especially cryptographic point of view, what are the threats, different real-time challenges for the industry purpose. And now I think it will be better if we can go to the lab for doing something in the hand, at least 1 to 2 subjects if possible. These are the things we will be doing in the lab.
Sir, what is G gate? G gate.
G gate.
G class B.
I have not used. There are so many things. I have not used. Have you used G gate? G plus B minus.
Is it a quantum gate?
Now we will do the first part of the session, and before next part will be in the lab, and before going to the lab, I am requesting our respected Robotics sir to felicitate our guest performer. Requesting Coleman to join. I am requesting Sarvani Sen and Somin Bhattacharya
Somin Bajpayee.
Somin Bajpayee, sorry, I am sorry, to come with us. Requesting HOD sir and Coleman to felicitate.
Somin and Sarvani will show in the lab.
So, requesting everyone to come to the lab.
that.